Okay, so I did this last Thursday, and I know it was right before the midterm. I will also sort of mention that we have, and I'm going to go crazy right now because of that door. I have a summary video that is essentially these slides. I'm going to add in a couple things here, but that's not terribly important right now. That's the summary of kinematics of rigid bodies, and I think chapter version 2. There we go. All right, there we go. And what I want to talk about really briefly is what we're doing in this chapter. So in this chapter, again, in the previous chapter, we started to talk about what happens when you have a rigid body. You have mass and size. And so what looks like Newton Euler's second law right here starts to apply. Sum of forces is mass times acceleration. And we're looking now at the center of mass. But there's a new term that appears, and this is something that you're going to deal with a lot of the course. And so the sum of moments is Ig alpha. Ig is the moment of inertia. And I went through a bit of effort to sort of rederive all of those terms, but alpha is the angular acceleration. And you can see that much like angular momentum and linear momentum, these have a nice analog. The only problem is this term right here, Ig. Ig is a term that is not absolute. Mass is absolute. Moment of inertia depends on distance. I'll talk about that in a second. There we go. I think in the process of getting the door locked on me, I haven't been able to figure things out. All right, so moment of inertia just generally is something that depends on distance. So for about the z-axis, r is a squared dm. I have a square rod, for example, with a distance r. Each of the individual masses are going to be rho dv. Rho is density, and this is something you've probably seen in a chemistry equivalent. But it'll have units of mass per unit volume. But r squared is something that is geometrically dependent, not absolutely dependent. So this one about the z-axis is going to be different than if I take that same moment of inertia for the same body and I try to calculate it about an axis that is parallel to the bottom of this mass. So I have r squared, I equals r squared rho v, or I have rho where it's usually a constant. So in a case like this where I have a long slender rod, just calculate it out and I get r squared dm from top to bottom. And instead of calculating it for everything, I can take a shell element or a disk element, take each of those disks and sum them up. I'm just integrating all the way across, up to the top to bottom, and I end up with r squared mass of the rod divided by its length, because that gives me kind of a kilograms per meter dr. And I end up with mass of the rod over 3L, L cubed over 8 minus L cubed over 8. And out of that, I end up with this 1/12 ml squared. And if you've been looking ahead in the text a little bit and sort of looking at what we're going to be doing, you'll notice that this is a pretty common one. So for long, slender rods, disks, and other shapes, these are documented, and you should be aware of what they are. In the last lecture, I also derived one of the other things that you need to know. So, sorry, maybe I'll just back up a tiny bit. You do not have to rederive everything every time. You do have to know certain things. So one of the things that you absolutely have to know is parallel axis theorem. You need to know moment of inertia for a long, slender rod, for a disk, and for a hoop. But I'll talk more about the hoop in a second. So parallel axis theorem, I have an object that has a mass center at G, and I want to look at, say, pinning it at point A, and I need to calculate the moment of inertia about point A. So I might want to calculate the moment of inertia about its center of mass of a compound system, center of mass, whatever. But here I'm just looking at point A. And if I do the integrations and do all of the terms here, IA equals R squared dm, I can write it as d plus x prime squared. And I did the right thing, y prime up. And so get R that way, and then do the integration. Once I've done the integration, I end up with R squared here from the center of mass. I have everything about x prime plus minus and d squared dm. And I end up with a system that if I want to shift from one point on the body where I have a tabulated value, which is something that's pretty common, to another point where I might not have a tabulated value, then I'll end up with ig plus md squared, d being the distance, the perpendicular distance from G to A. This doesn't go in reverse. You can't say IA or ig equals IA plus md squared. Everything is with respect to the center of mass. But you could say IA minus md squared equals ig. So one of the very typical cases you look at is an object, a linkage that is pinned at one point, and you want everything about point O. And so you know that you can say IO alpha is IG alpha MAG L over 2. MAG is the translational acceleration of the center of mass. And if you write it out that way, and recognize that if something is pinned at a point, and is rotating about it, then the acceleration g is just L alpha, right? And so if it's L alpha, then you can put that directly in, and guess what? You end up with the parallel axis theorem again. And so this is not something that is arbitrary, and it becomes problematic. Say, for example, if you have slip or something like that, it starts to fall apart. But in general, it's a useful sort of tool that you need to recognize has physics behind it. Now, the other thing that we talked about, and this is again important, you may not be given any information other than the radius of gyration. Again, that's a legitimate way to sort of ask you a question in this course. But say I have this crazy shape with all sorts of holes cut in it. I can say, look, the radius of gyration, the equivalent hoop of material, is one with a radius of k sub g. And I understand, now it's one of those things that's going to drive you a bit crazy, is that we're going to have spring constants of k, and now we're going to have radius of gyration. But you should know what the definition of radius of gyration is, and use it or know how to use it when you're solving problems. Oops. Oops. Wow, I'm covering everything from the last lecture. So in the last, again, we did composite bodies. Now, composite bodies are another one that's really kind of neat and useful to you. And so, for example, if you look at a composite body like this, you have a rod, a long, slender rod attached to a disk. Rod has a length L. Disk has a radius R. Center of mass of the disk is G disk. center of mass of the rod is g rod. So, right there. And you can do all of the same things as long as, and you can also define the center of mass of the system. You should know these equations. These we won't give you on an exam, but it's also a weighted average. It's not really hard to figure out. So mass of the rod, x rod, plus mass of the disk, x disk, where you've defined an xy coordinate, usually something like this, where x and y are here. So you combine those, put them together, and you end up with the x position of the center of mass and the y position of the center of mass. Okay, thank you. All right. So you have x disk. Okay. Now, the important point here is that you can then use the parallel axis theorem, and you really should know how to do the parallel axis theorem to figure out where exactly, or what exactly the moment of inertia of the pin is. So you add up 1/12 ml squared for the rod plus m rod times L over 2 quantity squared. Beyond that, you have the disk. And the disk is 1/2 mass of the disk, r squared, plus mass of the disk times r plus L to the pin, and that quantity squared. These are not hard. These are just, once you do them a couple times, it'll be very clear what you're doing. We talked a little bit about moments. Moments are essentially going to be a multiplier, or the effect of a force about a point of interest. And we've looked at this with angular momentum, where, for example, you have a force that's being applied out here, and we're just going to call that Ri and sort of O. And that causes a moment, and you need to know what exactly that translates to in terms of forces. And you can do that for a rigid body by adding up each of the particles and multiplying it, the force applied to it, by its moment arm, plus the sum of all moments acting on the system. So you'll often have a set of forces that are acting on a system. And we'll often say, hey, by the way, we've got these moments acting there. And in that case, what you want to do is not really try to describe hundreds, thousands, millions of particles. You just want to do everything with respect to the center of mass. And so you're going to take the resultant force, which is mass times acceleration g, the center of mass, times, essentially, or cross multiplied with r sub g. So the normal distance to the point of interest. And then Ig alpha is all of the moments. And you add them up and get everything together. What is important out of this is this final equation right here. You need to know that sum of forces in x is mass times acceleration g of x. Sum of forces in y is mass times acceleration g of y. Sum of moments about g, Ig alpha, and sum of moments about an arbitrary point on the body is just going to be the sum of moments about arbitrary points. Things get a little bit more interesting when you start to look at all of the same motions we had before. Now, motion is parallel, rectilinear, or curvilinear. These are straight line or curved path. Equations from particle kinematics still hold. And sum of forces in x is mass times acceleration gx, sum of forces in y, mass times acceleration gy, sum of moments about g equals 0. Now, you could also go normal and tangential and solve all the same thing. Where things get a little bit weird is when you have a point that is not the center of mass in a translating body. In which case, you will have a moment. So say, for example, I solve through and I have this object and it has a moment acting upon it. It's translating, with respect to the center of mass. But it is not 0 moment about point A. So when you do sum of moments about A, it'll be mass times acceleration g times the normal distance, again, d, to point A. This is all crystal clear. The important point here is that you can have moments when you don't look at the center of mass. All of this is with respect to the center of mass when you look at the previous bit right here. But when you look at this, we've shifted to another point. And because of that, we do have a moment at that point. So there's not a balance that you had before. Curvilinear translation, same thing as before. We have sum of forces in n, sum of forces tangential, sum of moments about g. And if we look at some arbitrary point again, off center A, we will have a moment. And that moment will be a combination of both the tangential and the normal components of the forces, or the resultant forces. So you can see lots of complicated motion that you're going to deal with, even with translation. And particularly to be very careful when you shift away from that center of mass. Rotation, not so bad. Everything sort of works the way it should. Sum of forces, you know, I have an object. Here I'm pinned at O and I'm rotating about. I've got a weight acting down. I've got point A. I've got point G, which is a center of mass. Point A is an arbitrary point. But sum of forces in N, mass times acceleration G normal, which we already know in terms of magnitude is omega squared RG. Now, I am just doing the magnitude at this point. I haven't put a vector in, but I'd have to draw that in and solve all of that. And it's the same thing with acceleration, RG alpha. Now, when I'm dealing with something that's rotating, I know the direction of it, and often I won't even do a vector calculation because it's really quick and easy. It's kind of one of those things that sort of go ahead. But I can, I can look at sum of moments about G, Ig alpha, but I can also shift it. So I can say sum of moments about point O, which is really more interesting, and often you will find in all of the sort of discussion that we have, we take everything about the point of rotation, because that is only rotating. Every other point in the body is rotating and translating. And often your goal when you're setting up these problems is not to make things more complex. Take the simplest motion and see if whether you can relate everything else to it. So you could do that with some moments about O, I naught alpha, which is Ig alpha MAT RG, Ig alpha MRG squared, alpha, which is, by the way, again, parallel axis theorem. And the really important thing to understand is, again, parallel axis theorem is not coming out of thin air. It's not just because I can sort of show you a mathematical relationship. There's a good physical link to it. And it's coming out of second law. Finally, everything's a lot easier. General plane motion, which is something that you will deal with a lot, is just going to be there. All right, so that was the last lecture in 20 minutes. Any questions? Go ahead.
I was just a bit confused, like when you said there could be moments about A, but even if the thing is
Translating.
Yeah.
Yes. Well, think about it this way. I have an object, and it's perfectly balanced. Right? And it's balanced about G. And that means half of the moments, half of the forces are sort of pushing it this way, half of the forces are pushing it this way. And it's all dependent on the geometry. Now, if I shift off to point A, I don't have that balance anymore. And so if I don't have that balance, that tells me my moments will not be 0 about point A, but they will about G.
But
because you'll have an acceleration, you'll have everything else. You still have the same body, but the sum of moments about point A will not be 0. That's all. So any point on the body, any particle can undergo a moment, but the entire body has 0 moment. It's a bunch of particles together, and then we got lucky because we chose the center of mass. Do I want to do this one? No. Oh, no, 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 no. Okay. I don't want to do that one. Maybe I want to do this one. Okay, let's start with this. And I have drawn it wrong for my notes, so that's going to drive me crazy. All right. Okay. I have a disk, and it's attached to a long, slender rod. And the rod, or the system, is rotating counterclockwise at 8 rads per second. The long, slender rod has a length of 1 meter. The disk has a radius of 0.25 meters. The mass of the disk is given as 15 kilos. The mass of the rod is 10 kilos. Find the reaction forces at O and alpha of the system. All right. So I have OY, OX, and I'm going to have to flip things around. And I have G of the disk and G of the rod. So I have a rod, I have a disk, I have forces acting. They're all kind of acting together, and they're all rotating about point O. All right, what do I have to do? I have L, I have my direction. I have counterclockwise because I have done this wrong. I, G, bar, alpha, and I, G, disk, alpha. And I have normal and tangential. So I have a whole bunch of forces that are acting on this. I have resultant forces and resultant moments that are going to come out of this. I have IG of the disk, I have IG of the disk alpha, I have IG of the bar alpha. I have also the reaction forces at the pin, I have the weights. Everything is sort of one composite system. Now, when I look at the normal acceleration, it's going to be a distance r plus L to point O. And because it's a distance r plus L to point O, I can do minus omega squared r, but I'm just going to write r plus L omega squared. For the acceleration tangential, same thing. I could write r cross alpha and alpha cross r. And if I do that, I'll end up with r plus L alpha. Same thing with the rod. Mass of the rod, acceleration normal, mass L over 2 omega squared, mass of the rod, acceleration tangential, mass L over 2 alpha. So if I do that, IG, or IO rather, is 1/2 mass of the disk times r squared plus mass of the disk L plus r squared plus mass of the rod times L squared. Now, I put the 1/3 in red just as a reminder that that again is a derived quantity, and I used and in the last lecture, we did a derivation for a pin rod. And it basically, you add in 1/2, you get a quarter plus a 12th, you end up with 1/3. So you end up with that. Okay, no problem. And we have all of the accelerations, we have all of the terms. We end up with a whole bunch of crazy terms. We're expecting forces in y, negative, is that good? Everything, oh no, I flipped the signs here. My example is reversed, so I'm looking at my example and trying to sort of correct everything simultaneously. So in this case, it's going to rotate counterclockwise, or it's going to rotate, well, it's saying it's rotating counterclockwise. So sum of forces in x, OX equals md L plus r omega squared plus mb L over 2 omega squared. And then finally, sum of moments about O, mdg L plus r plus mb L over 2 g equals I naught alpha. So this is really close to what you were used to when you were dealing with second law. Second law, you add it up, the important part, just 1 second. The important part was writing your free body diagram. And please spend the time to draw them out. Once you have that, you then have a group of equations and you can solve it. Go ahead. Oh, mass of the disk. Oh, a mass. That is an R. That should be, yeah, those are R's. Again, sometimes when I look at my notes, there you go, thank you have out of this a group of terms, you have everything you need, and from this you get OX which equals 1.52 kilonewtons, OY, which is 42 newtons, and alpha, which is 8.55 rads per second squared. Putting these equations together isn't, or solving the equations, those are not hard. If I put them as numbers, you do them right away. But what is hard is drawing that diagram. And spending the time on that is what you're going to find is the big thing. Whew, all right, that's correct. Oh, sorry. Any questions on this one? I will, okay, so this section of the lectures is done on Wednesday. So by the way, Wednesday we're going to cover all of second law. Thursday to Wednesday we will cover all of work energy. Thursday to Wednesday again we will cover momentum, including angular momentum of rigid bodies. Just one sec. No. It's so from Thursday this week to the following Wednesday, we are covering work and energy. From the Thursday next week to the week Wednesday 2 weeks from now, we are covering momentum. And then for the remainder of the course, we will be talking about vibration. So we got a lot to cover still. All right. Okay, these are really hard problems. Okay, these are not hard problems in the sense that once you write the free body diagram and do everything, everything is straightforward. However, one thing that I do find, especially at this stage in MIE 100, is that problems like this is really are really hard to follow and to accept. Because one of the things that you always want with a wheel is that it rotates about its center. The wheel has to rotate about its center, and it doesn't. No wheel in this course except, well, no wheel in this course really. We only have freewheeling wheels. We don't put axes or any type of axes on them. We don't do anything of that nature. But we have center of a wheel. Inner radius is 250 millimeters. Outer radius is 400 millimeters. You're given a mu sub k, which is equal to 0.15, mu sub s, which is 0.2, kg, and again, remember that kg here represents the radius of gyration of 0.3 meters, and a mass of the spool is 100 kilos. You have a force that's applied at the very top. And so before you begin this problem, before you do anything, sort of write in your notes which direction you think this will rotate. And why? So sort of put that in your head before you start this problem, because that helps you sort of understand why things get a little bit weird. So just pointing this out, the radius of gyration is there. Okay, so the next part, I have the force that's being applied. I have alpha and omega of the body. I have an angular acceleration because I'm pulling on it. There's G. I have a normal force, and I have a force of friction. And the total distance to the ground is 400 millimeters. And again, one of the things you should highlight in your notes is why exactly is that force of friction acting the way it is? The wheel is moving to the right, but it's rolling in a clockwise manner. And so because it's rolling in a clockwise manner, the friction force is opposing that motion. And at that instant, right now, in this part of the problem, we assume that there is no slip. So everything is sort of good. Okay, I've got all the forces. And you can see that as far as the forces are concerned, this is pretty straightforward. Nothing is really there. I mean, it's just, here's a set of forces that are applied, P, N, F, nothing major. All right. So we have no slip, and we start to look at it from that perspective. So I don't necessarily know that it's no slip. I do know that at this point in the problem that I'm going to assume it's no slip. I'll check that and make sure that that makes sense. Sum of forces in x, mass times acceleration, g in x. And so that is not so bad. P plus force of friction equals magx. Agx is equal to r alpha. And r is sort of the distance from the center, or from the center of mass to the point of contact. Because remember, this is no slip at this point. And because it's no slip, you're going to have a distance of 400 millimeters, 250 plus 150. One advantage I have in all of this is sum of forces in y is equal to 0, because often, or always, this doesn't sort of bounce. And where's my weight? Yeah. And if I have the weight, N minus mass of the spool times G equals 0. And I need to have, for this to hold true, mu sub s n. So I need the force of friction to be less than or equal to static coefficient of friction times normal force, because that's all I have. That's what's determining. Normal force is nice here. It's mass times G. Now, one of the things I've been trying to do with my examples is making sure that I stay with a consistent plus, minus, and rotation. And so in this case, I don't. So I have a clockwise rotation that's positive, which is not always good. But if I do sum of moments about G, I don't have to worry about the weight. I don't have to worry about the normal force because it has zero moment, or zero moment arm. It goes right through G. So the only forces that are applying a moment are going to be P, which is moving to the right, and friction, which is moving to the right. Now, that's easy because P times A, why do I have A? Okay. I'm going to call that A, and B, because I don't like to be consistent in my notes, plus mkg squared alpha, and there we go. Is that correct? P to the center of mass is causing a clockwise moment. So that's okay. So that I have defined as positive. The friction force, on the other hand, is causing a counterclockwise moment. And so this is one of the reasons why it's really important that you draw your own diagrams. If you don't, if you just kind of look at our diagram, you're going to miss some of this stuff. So this term right here is very wrong and should be negative. And so when you're looking at these problems, that's where you kind of stumble. And where the drawing the free body diagram is crucial for your success in sort of solving these things. All right, no problem. Now I have this acceleration. Oh, maybe I should do alpha first, then I can do alpha. Alpha, 1.3 rads per second squared. AG equals 0.52 meters per second squared. Normal force is equal to 98.1 newtons. Am I done here? I'm not done because I really don't know yet whether or not it's slipping or not. All I know is that for the set of assumptions that I have put in here, then I'm okay. I can start with this and say, okay, I've got 981 newtons. So force of friction based on this will equal 2 newtons. And force of friction max is mu sub s times n, which is 981 newtons, times mu sub s, which is 196.2 newtons. So force of friction is less than force of friction max. So if I get a question about rolling with and without slip, and I don't do that, even though I got the right answer, I haven't really solved the problem. So it's really, it's again, crucial to understand what you're checking for, and I'll do problems with slip later. But there you go. Any questions on this one? Oh, because at this point, I'm assuming that it is going to be no slip. So G is A sub G, it's R away, and it's, A sub G is this, and R G alpha. So it's as if it's rotating about a fixed point, but it's an instantaneous center of zero velocity, and that instantaneous center of zero velocity is the point of contact. So again, it's often useful to sort of define things with respect to that point that you know is not rotating. Any other questions? This is kind of a mid-step problem. We're kind of getting to the point where we're looking at sort of more complex geometries. Let's see what I have here. Disk, ball, energy, pulleys. I don't want to do, oh, this one. I do want to do this one. The other thing that's often challenging, and this is, I think, I know it's similar to a problem we did in the last few years. It would be on a final exam. I just can't remember offhand which one. But basically, these often one of the problems that you have with problems in the course is it's really hard to visualize things. So I have a 3.2 kilo slender bar that is released from rest, and you're asked to determine its angular velocity at that instant. And you have two cases. The surface is rough and the bar does not slip, and two, if the surface is smooth, which means that the bar will slip as it sort of moves. So no matter what you do, you have a normal force acting here, you have a friction force acting here. And I did good this time because I kept to a consistent notation. So x, y, and positive rotation is there, and the weight is acting down through the center of mass. And again, the only way you can solve rigid body problems is to assume that you can sort of look at it. So let's start with surface is smooth. And I will have 4 unknowns. I could probably use the same free body diagram for both parts of the problem, but for now you could just say force of friction is 0, so then it's just the normal versus the weight. Some moments about G, that's going to be N times L over 2 cos theta, which equals I G alpha. So it's 1/12 mL squared. And again, at this point, I know right away that when I'm dealing with a rod, its moment of inertia about its center of mass is going to be 1/12 mL squared. And I need an alpha there. Sum of forces in X is equal to 0, and 0 equals MAX. And I know it's 0 because there's no forces there. You want forces there. You want something there. But it's not rotating it. It's not doing anything. It's just dropping. So as it drops, you got sum of forces in X is equal to 0, 0 equals MAX, and that gives you right away an answer. Not maybe the most satisfying answer, but an answer. You can't put forces in that don't exist. So sum of forces in Y, on the other hand, I've got normal minus mg, normal minus weight, everything sort of works out great. I have mass times acceleration of y. Okay, there we go. All right. Acceleration of c equals acceleration of g plus acceleration of c with respect to g. So if I want to look at what's happening at the point of contact, which I do, I can just do that shift. Acceleration of g equals ax in the I direction plus ay in the j direction. Acceleration of c with respect to g is alpha cross r c with respect to g. There we go, that's enough. And alpha out of all of this mess will equal, after all the solutions, let me see, tuck. Anything else? No? Oh. AC with respect to G will be alpha L over 2 cos of theta. Substitute in terms, alpha is equal to, I've got 57 seconds, 6G cos theta, L times 1 plus 3 cos squared theta, and alpha is equal to 16.96 rads per second squared. And you'll notice that I do keep, just 1 second, I do keep in all of this my radians, and I use them as units even though I'm not going to call rad squared or anything like that. Go ahead. We're assuming an angular velocity of 0 because it hasn't started to rotate yet, as it's just being released. And so this is, again, one of those hard parts of all of the visualization that you do, is that you want something, as you let it go, to immediately have an angular velocity. It may not, but it has an angular acceleration.